Hey everyone, Tess here. Let's have a 1 hour talk about PKI, cryptography, certificates, all that magic, shall we? This is a talk I usually give at work or at ITVT where I teach every week. Just the fundamentals of certificates, cryptography, all that developers and starting sysadmins need to know. By the end of this session, you will hopefully understand the basics of cryptography, and you will also know why proper key management is so important. Cryptography involves lots of secret stuff, and you need to know how to keep that stuff secret. Aside from that, you will know what a certificate is and what they do, and you will also know all of the infrastructure that's needed to make all of this magical stuff work. And yeah, I'll finish off with a few best practices that every dev should know. Now, by this point, I'm going to assume that you kind of know how computers talk to each other. You know what a server is, what a client is, how do they do DNS lookups, what even is a DNS lookup, what's a host name. Basically, how do I get from Google to an IP address, and what does my browser do if it talks to a server like that? If you understand that stuff, we're good to go. If you don't, well, buckle up, we're going to have some fun. Okay, cool. Now, we're just going to start building off of concepts, stacking them all of on top of each other. Let's go have fun. Whenever cryptography is brought up, there's two things that any book, whether it's CISSP or CompTIA Security Plus or some PKI training, well, they all bring up two concepts. One of them is Alice and Bob, and the other one's the CIA. So Alice and Bob, they're older than I am. They're this proverbial couple of people who want to have secret communications, whether they're sharing cookie secrets, recipes, whether they're sharing love letters or nuclear launch codes. We don't care. They just want to have secret communications without anybody listening in on them. And as I said, they're older than I am. They're from a academic paper from the late 70s by something that should kind of sound familiar to you, RSA. RSA, ring a bell? Well, that's Revest, Revest, Samir, and Alderman, three smart people who did an academic paper on what we now call public key cryptography or asymmetric key cryptography. We'll get to that. Anyway, so Alice and Bob, always brought up when we talk about crypto. Plus, the CIA, in this case, not the creepy government thingy over in the US. No, it's confidentiality, integrity, and availability. As far as information security is concerned, those are three things that we think are worth protecting. Or actually, we have to protect them. We got to keep things secret, we got to make sure that nobody changes our data, and we need to make sure our data remains available, right? Cool. Now, cryptography, it can help us with the first two of those. We can keep things secret and confidential by enciphering the data, and we can guarantee its integrity by doing hashing and signing. But funnily enough, cryptography can only hurt availability. I mean, what if you encipher some of your very special data and then you lose the password or the keys? Now you can no longer access your data, so boom, no more availability. So, we're going to have a lot of keys flying around back and forth. And one of the things that we're going to try and prove with PKI is identity. Because it's great that you and I have key pairs and Alice and Bob have keys, but how do we prove that the key actually belongs to Alice or Bob and not some wily hacker in the middle trying to catch their traffic? I don't know. We're going to solve that problem. Because that's the point of PKI. Yes, it's about keeping things secret and guaranteeing integrity, but it's also about assuring trust. So what if we don't do stuff like this the right way, right? So what if we just start trusting keys willy-nilly? What if we do bad implementations of cryptography? Well, in the worst case, we get data leaks or data falsification. And that's not good. That's bad for everybody involved. Right. Let's start from the bottom. The encryption basics. Whenever we start talking about encrypting data, there's two different schools of thought that are most discussed. The easier one is this one, symmetric key encryption. That is a mathematical algorithm where both parties, in this case Alice and Bob, have the same shared secret. Whether they met before and wrote something down or whether they phoned each other, I don't know. They have the same secret key that they use in the mathematical function. So let's say Alice has this nice cookie recipe she wants to send to Bob. It's very hush-hush. She takes that message and she encrypts it with the shared secret. Now, if that message flies across the network and somebody listens in on it, it looks like garbage to them. They can't do anything with it. It's random binary data. But Bob, he can use his same shared secret key and decrypt the message. And that's great because now, boom, he can bake cookies, he's got the recipe. And thus we have confidentiality, at least as it's called, in transit. Because while the data is traveling between Alice and Bob, it's encrypted. But yeah, as I said, they need to share that secret key, right? How do they do that? They could phone each other. They could meet each other. Maybe share a USB key. That's cool, but what if they're on the other side of the earth, right? That's going to be tricky. Phone calls can be overheard. USB keys can be intercepted. And it's also going to be kind of hard when Alice phones Bob and says, yo, grab a notepad, here's 1,024 ones and zeros. Hope you don't make a mistake. So the problem that I'm describing is called key exchange. So we do want symmetric cryptography. Why? Because it's fast. Your computer CPU loves that stuff. It does it with 2 fingers up its nose. It's easy peasy. But key exchange. So how do we get to that? Well, there's, again, 2 big schools of thought on how to solve that. One of them is Diffie-Hellman, which is really, really cool stuff. And it involves some cool mathematics that can happen just out in the open. You and me, we could be surrounded by 20 people listening in, and I'm scribbling something for myself, you're scribbling something to yourself, then show everybody else, and you and me, we can still get to our shared secret key, but the rest of the people looking on are going like, I have no idea what's happening. It's so cool, I admit you, or I suggest you go look that up on YouTube after this one. Where we're going to go on is called public key encryption. That's the other way that was proposed to solve the key exchange issue. So, asymmetric encryption is what we're going to be looking at. Now in this case, both parties have a pair of keys. Alice and Bob both have 2 keys. And each of those keys in a key pair is irrevocably linked. You don't make a secret key and a public key. No, you make a pair of a secret and a private key. They go together. You can't mix and match between key pairs. It's one pair that goes together. Now what we're going to be doing is some cool mathematics that is kind of like a trapdoor, where if you encrypt something with one of the 2 keys in one key pair, you can only decrypt it with the other key from the very same key pair, or vice versa. So if, for example, I have a secret and I encrypt it with my public key, that's the P, becomes illegible, and I can only make it legible again with my secret key, but not with the public key. And vice versa, if I take a message and I encrypt it with my secret key, the only way of making it legible again is with my public key. Now the names of those 2 keys are a big hint already. Secret key, or private key as it's also called, is something you keep highly, highly secret. It's yours, you guard it with your life, nobody gets it. And your public key is something you can just throw out, give it to everybody, put it on a billboard near the airport. I'm happy. Millions of people can send me secrets. Right, so now if Alice and Bob want to start exchanging secrets, what they do is, well, first they make a key pair. And then they give each other their public keys. Bob gives his public key to Alice, Alice gives her public key to Bob. Now if Alice wants to send a secret to Bob, we're sharing secrets here, right? So she takes that cookie recipe again, She encrypts it with Bob's public key. Her own key pair does not come into play. When she's sending secrets to Bob, she uses Bob's public key. Message goes across the network again. Woo, nobody can read it. And Bob makes it legible again with his private key. And then vice versa, if Bob wants to respond to Alice, he uses Alice's public key to encrypt the message, and Alice uses her secret key to make it legible again. So now you know why you need to keep your private key or your secret key personal to you, not shared with anybody. Because that secret key is, well, key to reading all the stuff that's been secretly sent to you. Cool. So now we have confidentiality without the worry of key distribution. We have our public keys among each other, and if I want to send something secret to you, I use your public key. And this stuff is at the basis of a lot of stuff that you use in daily life. So that's pretty darn cool. Now, of course, there's the next issue. What if Alice one day gets an email from Bob that says, here's my new public key. And Alice says, oh, fine, this is Bob's new public key. I'm going to use this from now on. And then the next day Bob goes, I can't read this. And there's this wily little hacker cat that goes, ha, I know of your secrets, Alice. That's not fun. How do we guarantee that a key or key pair belongs to a specific person? That's the next challenge that we're going to be solving. So to do that, we're going to add a few more mathematical cool things. One of them is hashing. The other one is, well, we're going to work towards signing. Hashing you have probably already run into. It is a way of mathematically describing a piece of data with a very short string of characters. Letters, numbers, basically. Consider it a black box of mathematics, where if you open the box and you put in some data, block of data, a file, whatever, that box will start crunching and out poops a string of characters, letters, numbers, which describes what the data was, basically. And every time you would put in the exact same file, that little black box of mathematics would poop out the exact same hash, the letters and the numbers. But then if you change even a tiny little thing of the file that you put in there, the box goes ka-chunk, and oh wait, hang on, the hash completely changes. And this stuff is just readily available to all of you. Let's say I'm going to write a little letter, right? Right, so Alice wrote a letter. We could use MD5. MD5 is a command on Unix, macOS, Linux to calculate the MD5 hash of a file. So I'm going to do letter.txt, and it says, well, your MD5 hash of letter.txt is 2BOFA, etc., etc. And if I repeat that, out comes the exact same hash. I could also do SHA, where is it again? SHA-SUM, which is SHA-1, a different form of hashing. There you go, another string of characters, letters and numbers, which describes the file. And every time you would rerun it, out comes the exact same string of characters. Now let's change a tiny little thing in that letter. You know what? Let's add a tiny little heart at the end and say, hey, okay, let's calculate the hash again. I'm going to use SHA-1, and you will see that the small change we made in the file results in a completely different hash. Not just a tiny bit of a difference, hugely different. Now, where you might have seen this is if you went to a download site to grab like a Linux ISO image or something like that. Very often they also have, next to the link to the file, they have this thing that says MD5, long string of characters, or SHA-1 or SHA-2, long string of characters. Basically, you can use that to verify that the file you downloaded was not corrupted during the download, whether it's exactly the file that the vendor intended for you to have. This does not guarantee that nobody tampers with it, because theoretically, whoever tampers with it could also mess with the hash on the website, but in this case, we just want to make sure, did my download corrupt, yes or no? But we are going to work towards getting tamper-proof files, and that is through signing. Because now we can actually, with signing, do two things. We can A, prove that a file was sent by a very specific person and that it wasn't changed. So how? What if we use that hashing? We've already covered this one. What if we calculate a message's hash or a file's hash, and then we take that hash and we encrypt that with my private key? Alice wants to send something to Bob where she wants to make sure Bob knows it's really her. Nobody messed with the file. It was not changed at all. She calculates the hash of the file and she encrypts the hash with her private key. Now you might remember, anything encrypted with your private key is legible to everybody in the world who has your public key. And that's okay. So you don't use that for secret stuff, but you use it for signing, because that's what this is. Message hash calculated, then encrypted with your private key, meaning it was you, because you're the only one who has access to your own secret key. And now we've got integrity and non-repudiation, because this signature check proves that it was me. Okay, right, back to Alice and Bob. Let's say they have a contract that says, hey, we're going to do something for $1 million buckaroos, and she does not want somebody to pull a Dr. Evil and go like $1 billion. It happens. So Alice takes the contract and she calculates a hash. So that's the FX over here. I didn't have a better icon for that. Anyway, so she calculates the hash of the contract and then she encrypts it with her secret key. The contract in this case is not secret, so it'll fly across the network with that signature on it. And then Bob will do this. Bob will decrypt the signature with Alice's public key. So that's the black FX. And then Bob will also calculate his own hash of the file. And if the two file hashes match up, Bob knows A, the file was not messed with because the hashes are identical, and B, because basically he could decrypt the hash with Alice's public key. He knows it came from Alice because the only one who could have made the encrypted message was the owner of Alice's private key, i.e. Alice. So that's signing and hashing. Right, cool. So how does this get to identity proving? Well, certificates. Because what do you call it when somebody signs someone else's public key? Certification. Ta-da! A certificate is somebody's public key that was signed by someone else. All right, so I say someone else. You could theoretically sign your own public key with your private key, just from within the same key pair. That is a self-signed certificate. That is like me hopping on the train going to the airport for my flight to Zurich or Munich or whatever. And on my way to customs, I pass Starbucks, grab a napkin and a Sharpie and write on it, Tess. And then I walk up to customs and say, here's my passport. And they go like, yeah, no. Because that's what a self-signed certificate is. You just saying, yeah, this is me, I'm me, really, trust me. And your browser doesn't like stuff like that. If your browser encounters a certificate that was made by somebody who they don't trust, your browser will yell at you. And this is a warning, and I know a lot of people will say, no, I understand this. I just want to get to my site. Come on, get out of my way. Your browser is trying to prevent you from getting phished. Think twice. Right, okay, so we need somebody else to sign your certificate for you. Cool? Okay, well, could be you. You could sign my key pair, I could sign your key pair. We both have key pairs, right? Still doesn't work. Because you would grab a napkin over at Starbucks and put my name on it, and I would do the same thing for you, and customs would still go like, yeah, you're a couple of jokers, but could you get out of the line? You're holding up people. So how do we get to trusted certificates? We need somebody else. And that brings us to PKI, who can make trusted identity verifications for public keys, secret keys. public key infrastructure. That is the problem that we are solving now. So there is a possible set of solutions for proving that a key belongs to someone. Blockchain is always brought up, and yeah, right around 2018 I saw a academic paper which kind of looked cool for a blockchain-based solution. There might be other academic papers. I have not seen stuff like this out in the wild yet. So, not for us, not right now. We could do something called the Web of Trust, which is something we use for PGP, pretty good privacy. You might have heard that if you do encrypted emails. Basically, a Web of Trust is where certificate holders or key holders certify each other. Basically, what I described earlier with you and me making napkins for each other. Well, as long as my keys get checked by a lot of people, and they all say, yep, I verified Tess's identity, and these are keys that really belong to Tess, things should be okay, right? And you might have visited a technical conference once, and on the agenda, somewhere late in the evening, it would say, hey, here's drinks, here's a social event, and there's a key signing party. So what that usually entails is people from the Web of Trust bringing their passports, bringing the thumbprints of their public keys, and then over drinks going like, hey, could you check my identity? And then when you come home, could you please log into the PGP key server and say that you check my identity? And that's how it works. All evening we have drinks, we check each other's identities, and when I get home I go to key server, I said, yep, one upvote for this key, one upvote for that key, I really checked them, they're okay. It's a decent system, it works for interpersonal contact with email. It doesn't really scale well though, because I mean the company I work for right now, we've got like thousands of servers, tens of thousands of certificates. That's going to be a long evening. I could bring my web server doesn't drink beer, so no, Web of Trust isn't going to work for our technical infrastructures. So that does bring us back to PKI, which these days is still synonymous with the certificate authorities. So, certificates in this case, a trusted certificate consists of somebody's public key, identity information. Like on my passport, it has a nice photograph and it says, this is Tess, and from this country, etc., etc. That's the identity. In the case of a certificate for a computer, it would have a host name, IP addresses, DNS aliases, things like those. For your company key card, it would have like your Active Directory account, your email address, things like those. Plus it has metadata, like who made this certificate, where can we do some extra checks, what is this certificate valid for, what could I use these keys for, things like those. But then it is signed by a trusted third party, a TTP. And that TTP is the certificate authority. So in this case, Alice and Bob both have their public keys certified by a CA, as it's called. So this CA, there's a whole bunch of them. You have commercial, you've got governmental, you've got open source. You might know a few names on this slide. And if you're not from the Netherlands, some of them might look wacky. Staat der Nederlanden. Yep, that's basically the Dutch government. They have a whole bunch of PKIs. I bet your company has its own PKI, multiple maybe. Heck, you could build your own. Just for in your home lab, have some fun. It's cool. And yes, the companies that we will work for have their own PKIs. Well, why would you ask? Why would I go through the trouble of doing all that work? Well, for starters, getting certificates from a commercial party costs some money. Whether that's $5, $10, $15 per certificate, I don't really care. In the end, depending on how big your company is going to be, that's going to run up a big bill. Plus there's also, you might recall that I said certificates have identity information on them. Every time you get a certificate from a commercial party, you're telling them stuff about your internal networks. What are valid usernames, email addresses, host names, IP addresses. That's not really cool. There's a lot of cases where you do not want to tell people stuff about that. Cool. So we trust these trusted third parties for a number of reasons. In the case of the commercial parties and client software like our browsers, those parties work together in something called the CAB forum, which is the Certificate Authority and Browser Forum, where they make all kinds of rules and standards and agreements about security, identity checking, and availability, things like those. And if a certificate authority agrees that they will definitely uphold all of those agreements and they can be audited and they will be audited and they will prove that it all happened, then the browser vendors and the software makers will say, fine, if you, dear CA, make a certificate, I will trust it. And you can see all of this trust. We will get to it. So does this ever go wrong? Yes, horribly, because as you can imagine, if things go wrong with trust, it's like a house of cards and it goes kablooey and we're in trouble. One of the most famous cases was around 2011, I think, with DigiNotar. That was a CA over here in the Netherlands. And, well, they were big, they were doing good business, everybody happy. But along came the issues in Iran. Iran, they had political dissidents that were working against the government, and they were using Gmail to communicate with each other. And the government wasn't very happy about that because the browsers, they were using HTTPS and the emails were either just stuck in the same mailbox and they swapped information that way, or they sent email via Gmail to Gmail. Left or right, the government wasn't happy because they could not listen in on what those dissidents were doing. So what they were thinking was, well, you know, we want to do a man-in-the-middle attack. We want to make those dissidents think we are Gmail. How do you do that? By forging a certificate. What they had do was they hired some hackers, well, state-sponsored actors, and they broke into DigiNotar and, yep, you guessed it, they made certificates that says, yes, this is officially gmail.com. And those certificates were used in man-in-the-middle attacks against those dissidents, and that was not good, to put it bluntly. So we learned a few things from back then, and things have improved, absolutely. One of those things is certificate transparency, where certificate authorities are now bound to publish lists of certificates that they have created. And those lists include the names and the aliases and the identities for whom they create a certificate. And now a company like mine, we can monitor the certificate transparency lists of all CAs and go like, did somebody make any certificates that look like Unix Serious or like Tess? So it's like threat intelligence or something like that. And here we go back to why would you want to run your own PKI? Well, that certificate transparency list would also mean you're leaking your names, your identities to the whole world. Another thing that we introduced for, well, public commercial CAs is the CAA DNS record. Basically, on your domain, you can add an extra record that says, these are the authorized certificate authorities for this domain, and no other parties are allowed to create certificates. Is that foolproof? No, obviously not, but hey, small steps. So that trust of the CAB forum, where does that get recorded? Where could you be able to see it? Well, unfortunately, there isn't one standard solution. The general term for it is a trust store. It's the storage point for our trust. Just about every operating system has its own. macOS has keychain access, Windows has CertLM or CertMGR, Unix or Linux has etc TLS. Some browsers have their own trust store, like Firefox, and then plenty of applications also have their own. Many applications will kind of hopefully maybe look at the operating system trust store, but some also don't. Git is famous for fouling this up, NPM also, and just about every Java application as well. A lot of people will include their own Java key store for specific trust stores. Now, in macOS, we've got the tool keychain access. I have already opened it, and over here I can select the system roots list. That is basically the list of all certificate authorities that Apple has decided to trust. And there's a whole bunch of them. There's Amazon root CA, Apple root CA, who would have thought? There is Certinomis, no idea who those are. Chamber of Commerce, Komodo, DigiCert, etc., etc. I mean, you know, for something international, on an international level, this really isn't that much actually. But yeah, there we go. So on Windows, you could pop open CertLM or CertNGR and see what they trust. Firefox, it has its own certificates manager under the hamburger menu. That's where you'll find it. So if that trust store isn't complete and your client software tries to talk to something that it doesn't, well, something new, and it gets a certificate made by somebody not in that trust store, again, TLS will refuse to connect. We've already seen the pop-up from your browser saying, yo, don't do this. Well, command line tools like curl, which is in the text box, the first line, will give some less than user-friendly errors, going like, hey, there's a certificate problem, unable to get local issue or cert. Well, you could probably maybe piece together that, hey, wait, maybe this is about trust. Could be, right? Now, Java is a complete and utter, I was going to swear. It's a mess, let's put it that way. If you've ever seen Java applications crash, you will know that it's hundreds of lines of errors and code and whatever. And somewhere in the middle of those hundreds of lines, you will see something like this. PKI's path validation failed. And again, that's just your Java complaining, hey, I'm trying to talk to a server. Their certificate was made by somebody who I do not trust. They're not in my trust store. And yeah, I know a lot of people would say, fine, continue anyway. I don't care because I need my data. Please don't. That is you opening up yourself to phishing. So when do we trust a certificate? My client talks to a server. The server says, here's my certificate. Now my client does a whole bunch of checks. Most importantly, well, not most importantly, first and foremost, we check identity. If I go to Gmail and I get a certificate that says, hi, I'm for hotmail.com, something's fishy. So we're going to check, does the identity match who we think we should be talking to? It should be made by a CA that we trust. The certificate should not have expired. It shouldn't have been revoked, which we will get to. And there's something called a chain, which is important. So let's go take a peek at that. I've gone to Google. I mean, why not? I can inspect the certificate for Google by going like, hey, tap on the padlock, show certificate. And there's not a lot to see here, but I can pop it open, details. I wish I could make the window bigger. I can, good, there we go. So I have selected the certificate for google.com. And it says, well, the common name, the identity for whom this is valid is www.google.com. Well, I went to google.com, but maybe we'll find something that helps out. We see that the issuer of this certificate, well, they were from the US, and who is it? Well, it's Google Trust Services. What was their name? GTS-CA1C3. Cool, so that is the name on their certificate. Anyway, so what else do we have? Let's see. I'm looking for the expiry date. Have I missed it? Oh, there we go, at the top. See, I have to search every single time because all of these windows, depending on the browser, they will look different. So over here it says expires Monday, December 11th, 2023. Cool. Let's see, do we have something useful for you to see? Maybe a few things that we'll get to later. Now, what a lot of browsers do nicely is, hey, this certificate for google.com was made by Google CA1C3. You want to see their cert? Well, boom, here it is. I just clicked it in the same pop-up window. We have the certificate for GTS CA1C3. It is valid until September 30th, 2027. And in turn, this certificate was made by GTS Root R1. GTS Root R1, who's that? Well, that's this one over here. That is the Root Certificate Authority for Google Trust Services. And they have their own certificate because each of these things in the chain, because that's what this is, a chain, has their own key pair, their own certificate. So, do we need all of those CAs in our trust store? No, because if I go back to my keychain access and I go take a peek at the G for Google, let's see, Google, over here, there's only GTS roots. The GTS CAs in the middle, they're not here. What gives? Well, in your trust store, you only need the root CAs that are at the anchor, as it's called, of the chain. GTS root R1 is the end of the chain of certificates. It's the anchor, and that is what we trust. So in this case, we will trust the google.com certificate that I got because it's not expired. It hasn't been revoked, otherwise it would get a pop-up warning. Let's see, I'm looking for the aliases. Where's the aliases list? Sometimes these things are hard to read and I don't have my reading glasses on. Dang it. You've probably already seen it. You're yelling at me, Tess, it's there, and I can't hear you. Har har. Anyway, let's assume the name matches. It's not expired, it's not revoked, and it links back through its issuing CA to a trusted root CA that we trust. And if this whole chain consists of certificates that are valid, and it loops back to someone we trust, finally our client software will say, huzzah, I trust this thing, let's do TLS, baby. Oh, wrong window. Let's go. So the chain is a series of valid trusted certificates that link the subject, in this case google.com, back via the issuing CAs, one or more, to a trust anchor, the root CA. And once we bring all of this stuff together and my browser visits google.com, TLS will try and start to make a connection. The server gives a certificate and says, here you go, check it out, buddy. The browser or the client does all of those checks that I mentioned before. If it all checks out, the client and the server, the browser and Google, now have an asymmetrically encrypted channel. This is nifty. We now have a perfect secret channel. Nobody can listen in on this. Now, asymmetric encryption is slow, it's hard for your CPU, and we wanted to do symmetric crypto, right? Well, what happens is this. In this nice little secret channel that nobody can listen in on, my browser and Google will create their own temporary shared symmetric secret key. It's called a session key, and just for this particular session they will make a new shared secret key, and once that's done they will switch over to a symmetric algorithm, and boom, now they can do fast data transfer, and nobody listened in because thank you PKI, thank you asymmetric encryption. How lovely is this? So, in order to make all of this work, we need some more. We have trust and we've got encrypted data. It's all very, very good. But there's infrastructure that we need to make this happen. And two of those you already know, the subjects and the issuing CA. Subjects are Alice and Bob. They get their certificates, which are also called the leaf certificates, from an issuing certificate authority. Now, do they magically appear in their mailboxes, those certificates? No, of course not. In order to get those, Bob and Alice, they need to contact the registration authority. And when they generate their new key pair, they also generate something called a certificate signing request. And they send that to the RA, the registration authority, saying, please sir, can I have a certificate? And whether that RA is a person, some email box, a website, some API, we don't care, it does a few checks. Most importantly, are you allowed to request a certificate for the identity you're claiming? And are you definitely who you claim to be? In the case, for example, if getting a certificate for your domain, the registration authority might say, yeah, if that is your domain, you should be able to update DNS. So could you please add this text record to your DNS that has this very random string of characters, and then let me know if it's done. And then the RA will check your domain's DNS and go like, what do you know? It is in there. I guess you weren't lying, you really are managing that domain. Let's process that CSR. And it forwards it to the certificate authority, and that gives the certificates to the subjects, to your server. Cool. Now, we saw that the issuing CA gets its own certificate from somebody else. Everything needs to be certified. How else are we going to trust them? So in this case, the issuing CA, there's only one in this example, gets its certificate from the root CA. And guess who makes the root CA certificate? Well, that's the root CA. So I'm kind of backpedaling on never trust a self-signed certificate. In this case, root CAs are the only self-signed certificates we should ever trust. Now you can imagine that the private keys of certificate authorities are really juicy targets for attackers. Remember DigiNotar and things? Well, we usually don't have those key pairs just lying around on the CA. It's not just a file on the file system. Usually we use something called a hardware security module, which is, as the name suggests, a piece of hardware connected to the certificate authority. And that could be a simple USB key. It could be a desk-mounted USB device. It can be a rack-mounted device which talks to a number of systems in the network. No matter how you look at it, an HSM is this though. It is a piece of cryptographic hardware. It is not a general purpose computer, it is hardware specifically for doing cryptographic operations like creating keys, like encrypting data, and like signing data. And for the CA, in this case, the HSM gets connected and then the CA says, well, let's make my own key pair in the HSM. And then anytime the CA needs to sign something, like a certificate, it'll give that data to the HSM and says, dude, you've got my private key, sign this for me. And the HSM does it and gives the signature back to the CA, and the CA goes like, yep, cool, now I've made this certificate, very cool. So the HSMs, right, they're supposed to prevent people from stealing our secret keys. So then you might just think, okay, I'm going to steal the HSM. You just said it's in a USB key, right? I can pocket that. True. Usually, especially a root certificate authority, that's A, not network connected, B, in a highly protected server room, C, the root CA is just about turned off 95% of the time. It is not connected to a network even. It is tucked away in a safe, turned off, and the HSM is in a different safe, and you can't get to it. And when the root CA needs to be fired up, because hey, maybe the issuing CA needs a new certificate, then we need to bring a few people into the server room. Why a few? Well, we need something called quorum, a majority vote. The HSM often, of course not always, but often requires that, for example, 3 out of 5 people who have a specific smart card enter it into the system, give a PIN and say, yes, I agree that you should do this. That's cool. Okay, so maybe we have instead that network connected HSM, right? Rack-mounted hardware. That should be stealable because anybody can break open a network rack. They're not exciting. Okay, let's assume though that the network HSM has fired up and it's in there. If you want to steal it, sure, open up the rack, unplug it, put it under your arm, run away very fast. Well, that HSM usually has a battery backup built in, and it'll look at you and say, boy, brother, I hope you reconnect me to some real power because within 5 minutes I'm going to wipe myself. Erase. Self-destructo. All right, so some smart people might go like, okay, I'm not carrying it on my arm. I've got this nice little trolley here. It has a UPS, and I'm going to hook it back up. Well, the HSM will then go like, yeah, but hang on, you unplugged my network, and I don't know where I am right now. I'm going to lock myself again. Maybe even wipe if you don't put me back into contact with the other pieces of the network anymore. All right, you think, fine, maybe I will just really hard cut off your power, make sure the battery dies, and then I will just read the keys from the memory chips on the motherboard, right? Well, guess again, bucko, because A, the lid on that thing is tamper-proof, tamper-resistant, and if the HSM notices that you're popping it open, if the battery is still there, it'll go like, I'm wiping myself, dude, stop it. But even if the battery's gone, You cannot get to the storage chips on the motherboard because they're under epoxy. And that epoxy is made in such a way that if you chip at it and you try to get it off, you're breaking the actual chips. So HSMs are really cool stuff to work with. I really love them. You can get one very cheap one like a USB sticky or a smart card based HSM for like maybe $100. You can get very expensive desk mounted USB devices for like, what was the cheapest one I worked with? I think $4,000. Or you could start with a nice network HSM, and the cheapest one I worked with was 12K. Still, cool stuff. Not for your home lab maybe, but okay, HSMs. We got our CAs, we got our key secret. Wow, I was talking so long, my screensaver almost turned on. Right, next step. What if Alice left their laptop in the car and somebody busted it open, stole the laptop, and now we should never trust Alice's keys ever again? I mean, sure, she had them password protected, but we should kind of maybe count on the thief getting the private key and using it anyway. We should no longer trust her keys. We need to revoke her certificate. Well, in order to do that, we need a validation authority. Alice yells at the CA going like, oh no, my keys have been stolen, revoke them, revoke them. And the CA does that, and they publish something called the CRL, Certificate Revocation List. Basically just a file with certificate serial numbers saying these were revoked. Don't trust them. That can happen with stolen keys. It can happen with server decommissioning. Plenty of reasons why you could revoke it. Anyway, here's a list of keys you shouldn't trust anymore. And then if Bob gets Alice's certificate, he can go and check from time to time with the CRL, going like, hey, has this thing been revoked yet? And that is what your clients and your browsers will do as well. Once in a while, they talk to a new server, they go like, who made this cert? Let's download their CRL. See if this certificate is on it. And let's see if I can find it in Safari. As I said, I always get lost in those different windows. Details window, because every certificate has a nice little spot where it says, you want my CRL? Here you can get it. In this case, let us see, certificate IA, OCSP. Oh, here we go. No, that's not what I wanted. I tapped it and downloaded it. That's not what I want. Right, you can see my mouse wiggle, right? The CRL distribution point. Over here, the certificate for google.com says, if you want the CRL for my CA, which was CA1C3, well, here you go. Download it from crls.pki.goog/gts1c3. And that is just that list of serial numbers for certificates that were revoked by Google 1C3. Nifty. You can imagine, though, that for certain client software, especially in embedded systems, getting all of those CRLs might be a bit of a chore. And storage space and memory space can get cramped, and those lists can go big. And then you have to re-download them every few days. If Bob were an IoT device, he wouldn't like that. So maybe he wants something else. That is what OCSP is, Online Certificate Status Protocol. So instead of asking or fetching the CRL and then checking themselves, Bob is presented with Alice's certificate, and then he yells at the OCSP server. I'm like, dude, I've got this certificate serial number here. Is this still valid? And in this case, the OCSP server will yell back like, no man, don't trust it. It's revoked. And Bob will go like, ha, click, hang up. I am not listening to you. So that's OCSP. Requires a bit more hassle, because now every time your client gets a new certificate, sure, it'll trust it for a while after doing an OCSP check, but still, every new certificate, it'll do an OCSP call. Maybe there's something even better. Well, there is OCSP stapling, where Alice, from time to time, can request the OCSP server to give her a new pre-signed statement saying, yes, this certificate is still valid. Now, that signed response is itself not valid for very long, but it's enough to cover risks, right? And now Alice can go to Bob and say, here's my certificate, and here it has been stapled with an OCSP response as well. And then Bob or my browser can go like, yeah, you know what, looks good enough. So which of these three is best? There is no clear-cut answer. And can this go wrong? And is this a problem? Sure, yeah. As I said, downloading and caching CRLs takes time, bandwidth, and memory space, and storage space. So that's not always cool. OCSP is a privacy issue, because every time your client talks to a new server, it'll yell to an OCSP server, go like, hey, this dude is browsing Pornhub. Yeah, that's not fun. So the stapling thing is kind of cool, but then you have like this margin for error where a key or certificate could be revoked and your stapled response is still valid. And then what happens if both CRLs and OCSP get blocked? What does a client do then? That's an issue in and of itself, because, well, it depends on what the vendor defined or what you maybe configured. Sometimes you can configure it, and other times the vendor will decide, do you want me to hard fail if I cannot validate a certificate, or do you want me to just forge on and try later? It depends. It depends, and you're going to have to test your own software and figure out what it does. And if you're the developer, well, you make your choice. Not by yourself. Talk to your architects, talk to your product owners, see what their requirements are. Cool. And again, why do we trust all of this infrastructure? Well, because the people building this, running this, have given guarantees about security, about identity checks, about availability. They promise to do the right thing. And it's not just technical stuff. They've written bunches of procedures and policy documents. All of that stuff can be audited. And thus we say, yes, certificate authority, I trust you. I will now put your root CA cert in my trust store, and every time I run into one of your certs, I will say, good. Cool. Can we still go wrong? Defo. Let's look at a few. Right, so first a few on-path attacks, or man in the middle, where somebody wants to be in the middle between, for example, a client and a server, a browser and a website, and they want to act as if they're the website. Like we got the evil hacker cat, whether it's my cat, whether it's Burp Suite, whether it's Iran, I don't care. They're in the middle posing as Google in this case. Well, the easiest way for them to pose as Google and get away with it is if you click that button that says, proceed anyway, I don't care. You could do curl and set it to -- insecure or -k. You could configure your Java HTTP client library and say, just ignore TLS validation. And in all of those cases you're saying, I don't care if I'm phished. I don't care if my data gets stolen. I don't care if everybody reads my secrets. And yeah, that happens. Why? Because every bloody Stack Overflow post where somebody says, oh no, I'm getting a TLS validation error, what do I do? Someone says, oh, just disable TLS validation. Please, no, don't do that. There's lots of tutorials online that say, oh, you want a certificate? Well, make a self-signed certificate and then click the button in your browser that says do insecure. No, please don't do that. Ever. And tell your users as well, don't do this. Cool, okay. We have properly instructed our users and ourselves. We will never click that button again, and we will only make trusted connections. So now, the attacker could try and tamper with our trust store. It's possible, definitely, because lots of software has their own trust store, and my operating system has its own trust store, and maybe, just maybe, that malicious actor has a piece of malware that they sent me in a phishing link, which adds their own certificate authority into my trust store. And thus my browser will trust anything that the man in the middle shows them, because hey, it's made by a trusted third party. And yeah, this definitely happens. Lenovo had an issue with this a few years back where they did some marketing Again, almost swore. Some marketing stuff where they wanted to read your HTTPS traffic, and they added their own CA certificate into your trust store. Kazakhstan did this, or tried to do this against their civilians. They said, well, everybody, you must install this trusted certificate on your Android phone, your iPhone, your laptops, because we must read your traffic. Well, they didn't say, they left out the last part. You never say that last part out loud, but that's what they did. And then, well, heck, your company's internet proxy probably does this as well. If you're on your laptop or your workstation at the office and you're browsing Google, Gmail, CNN.com, I don't know, usually you do not have a direct internet connection. Your internet traffic for browsing goes through an internet inspecting proxy server. And that proxy server will sit in the middle of your traffic, and it will go like, yes, yes, I am CNN.com, I am, well, maybe not gmail.com, because that's private stuff and they will put an exclusion. Sure, yeah, I'm playboy.com, I am newsworthystuff.com, I don't know. Your browser on your workstation will trust that proxy server because those, well, call them wildcard certificates, were made by a party that your browser trusts, your company's own PKI. So in some cases this is perfectly normal and works as intended. In the case of your company, it's for data loss prevention. But in the case of Lenovo, Kazakhstan, or some malicious hacker, it's not so good. All right, so other example. Let's say there's an API at bank.nl and the software team that builds that software, they have a Git repository that has all the backend code, whether it's Java, Python, I don't care, and it has, hey, keys and a certificate, because hey, we need to deploy from Git, right? So why not put the keys and the certs with the code? What if somebody gets access to that? It happens so incredibly much. Well, now they're not even posing as you anymore. They are now you. Congratulations, the hacker is API1.bank.nl. And they could also just act as your API talking to a message bus on Kafka, to an Oracle database, or to some other API which says, hey, hey, you need to sign in using a certificate. Well, they are now you. Congratulations. Happens a lot. Recently even to Microsoft and GitHub. Not fun. And yes, of course, there's the DigiNotar-ish case as well, where somebody manages to actually break into a certificate authority, or in some other weird way manages to sneak a certificate in your name into their hands. And again, there you. DigiNotar, boom. This is definitely the hardest way of forging somebody's identity, but it still happens. Right, so finally, almost at the end, best practices that we can talk about. If you're building software, if you're building an infrastructure, a tech stack, whatever, make sure that if your company has a PKI, you trust that PKI. Heck, you know what? Instead of grabbing that big long list of certificates that in my case macOS trusts, or which Linux trusts, you could pare it down and say, my software will only ever see certificates from PKIs 1, 2, and 3. Will only include their root CAs in your trust store. And then make sure the trust store is also only writable to the intended parties. Maybe make it read-only, also fine, definitely, because then you can't tamper with it. If you make TLS connections, always validate your certificates, check the names, configure your HTTP client correctly. If you're running a service like an API, a website, have your own valid certificates from the proper CAs. And then if you have keys, put them in the right spot. Store them securely. So where could that be? For example, in, well, if you're in an Azure environment, use Azure Key Vault. If you're on premises and if you have something like HashiCorp Vault, put them in there. There's plenty of solutions. Heck, you could use an HSM, but that's going to run up a bill again. But you could, whenever you redeploy your software to the target server, include steps in your deployment pipeline or whatever that says, I'm going to fetch my keys and my certificate from the vault and install them. There is absolutely no reason whatsoever why any human developer otherwise should be able to get your keys, see your keys, whatever. They're in a vault. The deployment pipeline grabs them, deploys them with your software. And yes, make sure that you use proper algorithms and libraries that have been approved by the project team, by your company, whatever. Use Bouncy Castle, use, which one was it for Python again? I forget, but use a properly vetted library. Don't just grab random ass cryptographic libraries. Don't build your own one. Which brings us to stuff that you shouldn't. Do not trust random CAs. Don't have a writable trust store. You know who you should trust, so make it read-only. Do not ignore certificate validation, please. Please, please, please. Don't use self-signed stuff on your own servers. Don't put your keys in Git or on Confluence or on the wiki or on SharePoint. Don't keep them in your email, your workstation, whatever. And don't use outdated crypto. Use modern algorithms that were approved from proper libraries, and do not roll your own crypto. I'm sure you're a great developer. You must be a mathematical wizard, I'm sure. But please don't ever use that stuff at your company. Cool. Tiny little bit more. If you want to build your own PKI, sure, you could do a lot of things. You could have your private test bed, your home lab. Your company could have their own PKI. Heck, you could be a new commercial vendor and you have an external PKI. Fine. What you're going to build and how far you're going to go with all of those, the policies and the documents and the designs and all of the agreements, it depends on what you're building. If it's your home lab, if you're going to be a commercial CA, oh boy, this is going to take a long while. Anyway, you could just run a VM. Heck, if you want to have a simple CA, you could just use the OpenSSL command. But it's a lot of fun to play with something like Active Directory Certificate Services, ADCS, and make maybe even a multi-tier CA, like a root CA and an issuing CA. That's a fun project in your home lab. Anything more serious, use a physical offline root CA, never ever ever connected to a network. Could be a laptop, but put it in a safe, use the proper procedures, policies. You have split quorum where you need multiple people, your root CA trusted like it's holier than whatever. Have proper stuff. We're talking about trust here, right? Don't mess it up. And yes, if you're going to build enterprise solutions, get a solid HSM. And every CA should have a HSM. Ensure high availability for your validation authorities, for OCSP. Do audits regularly. Have logs collected off server so they can't be messed with. Have somebody actually architect a proper design. And then, yeah, when validation fails of certificates, remember CRLs and OCSP, when that goes tits up, everything goes. The world becomes very wobbly. I'm not saying it'll fail right now, but it'll fail once your CRL cache expires, once that nice OCSP staple thing expires, once your client goes like, I haven't tried OCSP in a while, let's do it again. And then slowly but surely that house of cards is going to start wobbling and topple. It's not fun. There's a whole great talk by Mark Cooper, aka the PKI guy, who's got the top 20 mistakes in Microsoft PKI. If you want to learn more about this stuff, highly recommended. And I think that is about it. Yeah, oh yeah, you could use OpenSSL or ADCS. You could look at CertMonger, EGBCA. Cool stuff to play with. And that is about it for today. It says lab. I'm not going to make you do a lab. This is for my ITVT students. I think this was well over an hour. I'm going to thank you for your time. I hope this was worth your time. If you have questions, put them under here in the comments or drop me a line on Discord. Take care.